A 2025 Department of Energy analysis warns that annual failure hours across America's power grid could surge from 8 to over 800, a hundred-fold increase. 70% of the system's major assets have already outlived their designed lifespan, and after years of flat demand, load is now rising faster than at any point in a generation. The grid isn't just aging. It's being pushed toward a threshold it was never engineered to cross. In the post-war decades, engineers constructed the American grid with a simple design: move electricity in one direction, from massive centralized power plants straight to homes and factories. They designed major components like transformers and lines to last between 25 and 40 years, expecting predictable, slow load growth. Today, that entire foundation operates past those limits. Over 60% of the system's high-voltage circuit breakers have now exceeded 30 years of service. As mechanical fatigue and heat accumulate, physical age transforms from a routine maintenance checklist into an active reliability threat. Forcing this outdated architecture to carry the heavy demands of a highly electrified society creates constant operational stress. Recognizing this systemic decay, the American Society of Civil Engineers downgraded the nation's energy infrastructure to a D+. The physical grid remains frozen in the mid-20th century, even as modern economic demands continue to accelerate. After decades of flat electricity consumption, U.S. utility planners and the Energy Information Administration have abruptly revised their long-term forecasts. Recent EIA and utility planning updates show projected electricity demand rising between 15 and 25% by the mid-2030s. This sharp reversal of a decades-long stagnant trend is driven by three simultaneous shifts: the electrification of heavy industrial manufacturing, the rapid adoption of residential heat pumps, and millions of new electric vehicles drawing power from local distribution networks. Utilities and regional planners are rewriting their capital budgets because the next decade looks entirely different from the last. This surge will collide directly with physical assets that were never rebuilt for a new growth cycle. Consequently, the grid's physical age becomes an immediate, live operational constraint. The sudden surge in electricity demand does not spread evenly across the country. Instead, it concentrates in specific geographic corridors, turning a macro trend into intense regional crises. Recent Department of Energy analyses warn of 50 gigawatts of new, highly concentrated load driven exclusively by artificial intelligence and hyperscale data center expansion. Private developers are clustering these massive facilities in areas like Northern Virginia, Texas, and Arizona, where local grids were never designed for gigawatt-scale density. Because the American power grid is a patchwork of local and regional systems rather than a single, fluid national pool, these hotspots face immediate capacity limits. Company filings from 2025 show that while a data center can be built in under 2 years, upgrading the local substations and transmission lines to power them often requires 3 to 5 years. This mismatch means massive electrical demand is now arriving far faster than local grid operators can physically adapt. Extreme weather does not create the grid's underlying vulnerability. It exposes it. Meteorological data from NOAA and utility databases reveal that weather events have driven roughly 80% of major American power outages since the year 2000. When severe heat waves, hurricanes, or winter storms strike, they act as diagnostic stress tests, turning latent physical wear into immediate, visible failures where system components are already pushed to their limits. In 2024, Hurricane Beryl illustrated this systemic weakness, knocking out power to millions in Texas and costing utilities an estimated $1.3 billion in direct damage and restoration costs. These intense atmospheric shocks flood substations, reduce transformer cooling margins, and cause sagging lines to fault. Post-event analyses from regional operators show that as no AA records continue to register extreme conditions, restoring a compromised network becomes more expensive and harder to guarantee. Next time, transforming routine seasonal weather into an active threat to national reliability. The physical survival of transmission lines under severe weather is only half the challenge. The other half is expanding them. Generating power does little good if there are no high-voltage wires to carry it to consumers. Today, the nationwide interconnection queue, the official waiting list to plug new generation into the grid, exceeds 2,600 gigawatts of capacity. Regional transmission organizations and utility regulators face a massive administrative backlog, with the mean processing time for an interconnection study stretching to 35 months. Under current permitting conditions, a developer can construct a clean energy project in under 2 years, but securing the regulatory approvals and cross-jurisdictional permits to connect it to the regional network takes nearly 3 years. This structural mismatch means that while supply exists on paper, the physical infrastructure remains years away. Because demand growth is no longer waiting for the grid to catch up, this administrative bottleneck shapes every subsequent modernization challenge. Even if physical transmission lines are built, the fundamental way electricity moves is undergoing a radical shift. For a century, utilities operated on a simple hub-and-spoke model. Massive centralized power plants generated electricity and sent it in a single direction down to passive consumers. Today, that linear flow is obsolete. In 2024 alone, the system integrated 36 gigawatts of solar capacity and roughly 30 gigawatts of battery storage. These resources, along with millions of local rooftop solar arrays, turn former customers into active power generators. Distribution planners and grid operators must now manage two-way power flows on circuits built exclusively for unidirectional delivery. The core challenge is not the renewable energy itself, but an operational structure whose control systems, sensors, and physical hardware are still catching up to this multi-directional reality. As this architecture shifts, managing the grid is no longer about moving bulk power in a straight line. It is about constantly balancing a highly fluid network where electricity can flow from any direction at any moment. The Department of Energy estimates that power outages cost the American economy roughly $150 billion annually. This financial toll translates grid vulnerability from an engineering problem into a macroeconomic constraint. Precision manufacturing plants require steady voltage to prevent ruined product batches, while hospitals depend on uninterrupted power to maintain life support systems. In logistics networks and data centers, even momentary outages disrupt supply chains and digital infrastructure. Federal Reserve analyses indicate that power reliability now dictates where corporations invest capital, meaning a fragile grid directly caps national productivity and shapes future industrial growth. The response to this system-level crisis requires coordination across transmission expansion, faster permitting, storage, automation, microgrids, and demand-side management. While the Infrastructure Investment and Jobs Act allocated $73 billion for modernization, the scale of the required build-out dwarfs current funding. The Department of Energy's Office of Electricity requested just $193 million for fiscal year 2026, a 31% reduction from the previous year. This leaves a massive funding shortfall. The projected investment gap through 2033 stands at $578 billion and could rise to $702 billion if federal support lapses. The central issue has shifted entirely to pace. A July 2025 Department of Energy Reliability Assessment maps this timeline through 3 distinct scenarios. The baseline case projects annual loss of load hours near 8. But if 50 gigawatts of AI-driven demand collide with 104 gigawatts of planned power plant retirements, loss of load hours soar to 818. Preventing this requires a rapid build path that holds reliability to 2.4 hours or less. In this timing test, delays turn grid reliability into a direct constraint on national growth. The electric grid is no longer just a utility. It is the physical constraint on American innovation. As the race for AI and electrification intensifies, our future remains bound by a system designed for the past. If we cannot modernize, we cannot compete. Share your thoughts in the comments. Every crisis begins as a crack, small enough to ignore until it isn't.